Okay, let's start this one with an example. Let's find the integral of 1 over x squared from -2 to 1. Okay? Well, let's see. We learned back in Calc 1 how to find the antiderivative. This is x to the -2. So we add 1 and divide by it. So the antiderivative is going to be x to the -1 divided by -1, which is the same as -1 over x. So the antiderivative is going to be -1 over x. Evaluate from -2 to 1. And we're going to get -1 minus, sticking a -2 here. And you're going to get what? -1 over -2 is +1/2. Too many negatives there, and you end up with -3/2. -3/2. Is that right? Is that what I got the first time? Yes, it is. Okay, very good. So everything done nicely and in order, and we get an answer. Does that answer bother you at all? Think about what this function looks like. 1 over x squared from -2 to 1. The function is always positive. We're going from left to right. Why do we end up with a negative answer? The answer is we did it incorrectly. Okay, notice that this is a function which does not obey the rules needed for finding antiderivatives. We need something which is continuous and therefore bounded on the closed interval here. And this thing is neither continuous nor bounded. Well, in particular, bounded. It's not bounded on that interval. It heads off to infinity. So we can't do it that way. What we can do, though, is to do something similar to what we did before. Let me break it into several steps. The problem was at 0. So here's what we're going to do. We're going to first of all say that this thing is equal to the integral from -2 to 0 of 1 over x squared dx plus the integral from 0 to 1 of 1 over x squared dx. Okay? So we're breaking it up into the two parts, and then we'll evaluate each one separately. Okay, that's a little bit of the problem done. Now we need to know how to evaluate this, because it still blows up. Let me draw it up here again. It still blows up at 0, right? So we don't have anything that says that we can evaluate it from 0 to 1, because all of our theorems had to do with continuous functions on closed intervals. This thing is not continuous. It blows up there. So what do? Well, let's do something similar to what we did with intervals going off to infinity. We're just going to look at this thing right here now, and we're going to take this thing and we're going to write it like this. We're going to define this. We're going to define this to be the limit of the integral from, let's say, a to 1 of 1 over x squared dx, and then take the limit as this is from a to 1. Here's 1 right there. Here's a. And then we're going to take the limit as a goes to 0. The limit as a approaches 0, I guess, from the right. Agreed? So there we go. Same sort of thing we did before. We write this, we define it in terms of two things that we already know. We know how to do this integral, and we know how to take limits. So let's see what happens if we do that. So first of all, we're going to get, let's write limit as a goes to 0 from the right. The antiderivative is -1 over x from a to 1. That's going to be the limit as x approaches 0 from the right. I'm sorry, as a approaches 0. As a approaches 0 from the right of what happens when you stick in 1 here. you're going to get negative 1 over 1, which is negative 1, minus, when you stick in a, it's going to be plus 1 over a. And now you ask, what's the limit of this thing as a goes to 0? Well, as a goes to 0 from the right, this is going to get arbitrarily large, and so that limit goes off to infinity. Okay? So in other words, the area from 0 to 1, if you were to put any value to it at all, you'd say that this thing is infinite. Okay? It blows up as some of the ones that did before when we went off on an interval that went to infinity. Okay? So, there it is. There it is. And this one would do similar. It would blow up from there to there. So, let's keep that in mind. Let's do a couple others. How about 1 over x dx from 0 to 1? Okay, that of course looks like this. So if we go from 0 to 1, we can do it the same way. We can say, okay, this is the limit as a approaches 0 of the interval from 0 to from a to 1 of 1 over x dx, and that's going to be the limit as a approaches 0 from the right. This is also from the right. And the antiderivative is going to be the ln of x from a to 1, which is the limit as a approaches 0 from the right. The ln of 1 is equal to 0, and then the ln of a minus the ln of a. What happens to that? Well, what does the ln of a look like? Here's the ln of x. As you go to 0, that goes to minus infinity. So this thing here is approaching minus infinity with a minus in front. It's going to go to positive infinity. So what do you know? That thing also blows up. The area underneath that thing from 0 to 1 also blows up. Okay, goes to infinity. Well, heck, does everything do that? Let's try another one. How about 1 over the square root of x? Okay, it has the same look to it again. It's going to look like this. And already here, well, let's first of all, let's go ahead and do it one more time. So I'm going to say this is equal to the limit as a approaches 0 from the right of the integral from a to 1. And I'll go ahead and write this as x to the minus 1/2 power dx, which is equal to what? The limit as a approaches 0 from the right. Antiderivative of that is going to be x to the 1/2 power, which is the same as the square root of x, divided by 1/2. To divide by 1/2 is the same as multiplying it by 2, and then go from a to 1, which is the limit as a approaches 0 from the right. Stick in a here, you're going to get 2 square root of a, or 2 times square root of 1 rather, 2 times square root of 1, minus 2 square root of a. As a goes to 0, this thing goes to 0, we just end up with 2. Aha! So there are some of them that do converge. Why did this one converge, and why did it converge to 2? Okay, and again, I challenge you, turn off the video and try to think about it on your own. See if you can figure out both of those answers. Why could we have expected this one to converge, and why could we have expected it to converge to 2? Okay, I'm going to answer them right now, so as I say, I'll challenge you to try to figure them out on your own. When we took functions that went to infinity, as x went to infinity, then the one that did converge was 1 over x squared. Remember that? Y equals x squared. That converged. That looked like this. And this was finite. And then it went like this. Okay, went up there. On the other hand, let's get another color chalk for this one. Or color marker. Y equals 1 over the square root of x. That, if you were to graph the two of them together, that looks like this. And it looks like that. See that? Here's the point 1 right there. There's the point 1, 1. So notice what's going on. What's going on? These two things are inverse functions. So basically, this graph right here, underneath 1 over x squared, corresponds to this graph right here, underneath 1 over the square root of x. So the fact that this thing converged on this interval would suggest that this one is going to converge on this interval from 0 to 1. Alternately, 1 over square root of x did not converge on this interval, and similarly 1 over x squared did not converge on this interval. Okay? So that answers most of it. Then finally, why did it converge to 2? This thing here, when we evaluated 1 over x squared dx from 1 to infinity, if you recall, that converged to 1. This area right underneath there was 1. And so similarly, this area right there is also 1. But we integrated from 0 to 1, so we not only have that tail the same as we have here, but we also have this region right there, which is a region of area 1. So that's why this thing converges to 2. Converges to 1 more than this one, because you've got this box plus that right there. Okay? Lots of neat stuff there. Okay, if you understand functions, lots of neat stuff. And finally, the other thing you should notice is that 1 over x is the unique graph which diverges on both of them. Okay, there's 1 over x right there. So 1 over x is infinite on both of those intervals. Sorry about that. As I've mentioned before, for whatever reason, even though I'm using an Apple software on an Apple product, it crashes on me from time to time, and it crashed there before I realized it, and I erased the board. So anyway, let's go on. That was basically all I wanted to say about that. Here's what I wanted to say next, and that is that if you do have something like this, then notice that there are two possible places where it could blow up. It could either blow up here or it could blow up there as you go off to infinity. So the way to do something like this is to break it up into two intervals, go from 0 to whatever you want. Let's just say 1 again, 1 over x squared dx, and then go from 1 to infinity, 1 over x squared dx, and break it up into two different intervals. Okay, very good. Let's also look at this as an example. There's lots of little things to do here. What if we looked at this integral, negative 3 to 3 of 1 over x dx. Okay, negative 3 to 3 of 1 over x dx. What's the value of that? Let's again look at our function. It looks like this. And so if you do what I just suggested now and you break it up into two pieces, you could break it up into the integral from negative 3 to 0, and then add to it the integral from 0 to 3, 1 over x dx. And if you did that, you'd get the same result I got a minute ago, namely that when you try to evaluate this and you go to 0, it's going to diverge to infinity. And so that's going to diverge to infinity here. This one, for similar reasons, is going to diverge to minus infinity. Okay? So, what happens when you add them together? And there's two schools of thought on this. One school of thought is what I just mentioned to you, that if any part of it diverges to infinity, then we say the whole thing is divergent or no limit, whatever phrase you want to use, but basically you can't attach a number to it. So you'd say no limit or diverges here. The other school of thought is that this is an odd function. See this? From -3 to 3. And it, what do we know about odd functions? This area here is going to be exactly the same as this area here. This one is positive and this one is negative. So it seems like a very reasonable answer would be to say that this thing is equal to 0, because those two cancel out. Certainly, if we had sine of x, for example, from -a to a, those are all going to cancel out. Okay, so you can just say the integral is 0. Why not here? Well, as I say, they're both valid choices. It's just that the mathematical community has more or less rallied around this one, because for various reasons probably. One is that just in general, if you have two things that go to infinity, in general, if you have a situation like this, we learned this when we talked about L'Hopital's rule, then you really you need to be careful of it and not be too fast about attributing any value to it. But probably more important is the idea that this could be used, for example, by an engineer who's trying to figure out what's the force on an object, and maybe they're looking at maybe some sort of a huge object out in space where you have force both on this side and on this side. Maybe it's fixed right here, and you're kind of wondering, is it going to stay stable, or is it going to start going in one direction or the other? Well, as long as this is a finite number right here, 5 on this side and 5 on this side, we'll call this one -5, yeah, that's fine. Then you'd say, oh, okay, this thing is going to stay stable. It's not going to move, okay, and that you'd be getting the right answer. But what if situation in space was such that, whatever, it's getting closer and closer to the sun or to a black hole or whatever else, and this is blowing up and this is also blowing up? Well, okay, they are staying the same, so in one sense you'd say, okay, this is going to stay stable, but you'd kind of want to know about it. If these things were both blown up to infinity, the fact that someone told you that the answer was 0 is really not giving you the most important information. Really, the most important information is that they're both diverging, they're both going to infinity, and this thing might collapse, might disintegrate under the force of these things. So I think my guess is it really comes down to kind of a practical use, that if anything does go to infinity, you really want to make that very, very clear, and the best way to do it is to say that this answer is no limit, rather than to say the answer is 0. But there are people who say this. There are people that say that this thing, by definition, that this thing from -3 to 3 of 1 over x dx is equal to the limit as a approaches 0 of the integral from let's see, how did I want to do this? From a to 3 plus the integral from -3 to -a, and you keep those together. so that this value and this value are exactly the same, one being the negative of the other, and then as a goes to 0, this answer would be 0. I think that's called the Cauchy limit, if I'm not mistaken. Or Cauchy Principle Value. That's what it's called, Cauchy Principle Value. So it's just another way of thinking about limits such as this. Okay, anyway, let's go on and do a few more. What about this one? Here's an interesting one. Need to get myself another marker here. I still grew up in the days of chalk where you knew exactly how much chalk you had left. Okay, there's one. What's the value of that? And again, remember what the logarithm function looks like. Looks like this. So this thing goes down to minus infinity as x goes to 0. So we can go through the process of saying this is the limit as a approaches 0 from the right of the interval of the integral from a to 1 of ln of x dx, and do it that way. But I'm going to save some time, just like I did on the other ones. I'm going to save some time we're just going to realize that when you stick in the 0 here, you're performing that limit in your mind. So let's just go ahead and do this one kind of the lazy way. And you remember how to do it? The way you do this one is by doing integration by parts. And by letting u equal 1. No, I'm sorry. U is equal to the ln of x. Du is equal to 1 over x dx. Dv is equal to the rest of it, 1 dx. And so v is equal to the antiderivative, which would be x. Okay? And so what do we get now? Remember what the integration by parts says? It's uv, so it's going to be x ln of x minus the integral of v du. V du is just going to be x over x is 1, just going to be dx. So that's going to be x ln of x minus x. So there it is. And now, instead of going through all this limit of a stuff, we just go ahead and just stick in 0 to 1 right there, and 0 to 1 right there. We could combine them all together too, it doesn't matter. Let's just do them separate. So what happens when you stick a 1 in here? You're going to get, you know what, let's just do them together. That might be just as easy. Combine them together like this. So what happens when you stick a 1 in here? 1 times the ln of 1. The ln of 1 is 0, so that's going to be 0 minus 1, so it's going to be minus 1. Now subtract what happens when you put in 0. So you put in 0 here, and notice what you're going to have. You're going to have this thing times the ln of x as x goes to 0, and then you're going to get minus 0 here. Well, minus 0 there is no problem, but how do I go about evaluating what's the limit of x ln of x as x goes to 0? Let's see. This thing is going to 0. This thing is going to minus infinity. What do you do in a case like that? There's another call for L'Hopital's rule. Remember how to do it? You write this as limit of the ln of x over 1 over x as x goes to 0. X is going to 0 from the right here. It's the only way you can go. Now it's of the form minus infinity over infinity, so we can use L'Hopital's rule. Put a little L there for L'Hopital's rule. You take the derivative of the top. First of all, here it's the limit as x goes to 0 from the right. the derivative of the top is 1 over x. The derivative of the bottom is negative 1 over x squared. Limit. As x goes to 0 from the right, bring this up. You're going to get x squared over x, which is just x. It's going to be just minus x. And what happens to that as x goes to 0? That just goes to 0. So there you go. So you can't just throw in a 0 here fast and ready, because that's a 0. You had to use L'Hopital's rule here. This could have been anything for an answer, but it does turn out to be 0. And so we end up with negative 1 as our answer. So there's negative 1 right there. Okay? Very good. Let's try one more kind of regular one, and then I'll give you a couple interesting problems to do. Okay? What about the tangent of x from minus pi over 2 to pi over 2? What does tangent look like? Looks like this, agreed? Pi over 2, negative pi over 2. Again, someone could argue that this is exactly the same area as that. One of them is negative, one is positive. So as you head out from 0 to pi over 2, if you defined it this way, if you defined it as the limit of the tangent of x dx from, let's say, negative a to a as a approaches pi over 2, so that this is always going out at exactly the same rate that that is going, then no matter what a is, you're always going to get 0 for an answer. So this whole thing here would be just the limit of 0 as a approaches pi over 2, which is 0. So that would be the answer using the Cauchy Principle Value. Okay, Cauchy Principle Value, this would be it. However, as I just told you, the way that is standard to see this instead is to say, nope, this is the integral from negative pi over 2 to 0 of tangent of x dx plus the integral from 0 to pi over 2. And again, you wouldn't have to let 0 be your middle point, but it's just as easy right there. And then you have to do each one separately and see which each one separately is. If they both end up being finite numbers, if this is negative 7 and this is positive 7, then you can add them together. Negative 7 plus 7 is equal to 0. If they end up going to infinity, so that this is minus infinity here and this is positive infinity here, then you're going to have to say diverges. So let's see what happens. So first of all, what's the antiderivative of the tangent? Let's see. Let's just go ahead and do it. Tangent, of course, is the what? The sine over the cosine dx. And the derivative of the cosine is the negative sine. So I can put a negative here and also a negative there. Then that's the negative of the ln of this. ln of the absolute value of cosine of x. There's the antiderivative from 0 to pi over 2. So what happens as x hits those two things? Let's see. At pi over 2, what happens? The cosine, see how important it is to know what all your trig functions are? Here's pi over 2 right there. As you approach pi over 2, the cosine approaches 0. So this thing right here approaches 0. What happens to the ln as that thing approaches 0? You have to know what the ln function looks like. As this thing inside here goes to 0, the ln goes to minus infinity. I have the negative of that, so it's going to be going to infinity there. Okay? What happens when you stick in 0? Cosine of 0 is 1, the ln of 1 is 0. So it's just going to be either plus or minus 0, doesn't matter. The point is, it's infinite. That's an infinite area right there. infinite value to the integral. This one would be negative infinity, but we don't combine them to get 0. We just say it diverges. There you go. Okay, very good. I think I've done all the ones I want to do except for one. Here's a super interesting problem. I guess I should have done this in one of the previous lessons, but I'll do it right now since I forgot. Gabriel's horn. Okay, here's Gabriel's horn. You know who Gabriel is? Gabriel, I guess it's a he, is a angel talked about in the Bible, which I think proclaimed the birth of Jesus of Nazareth, and maybe showed up a couple other times in the biblical record. Anyway, if you know what a bugle or a horn is something that kind of looks like this. If you've ever seen a movie of Rome or Caesars and things like that, you got these really long horns that look like this. Well, Gabriel's horn is one that never stops, okay? And so here's how you get it. You start with a function y equals 1 over x, and you start it on the interval from 1 to infinity. So it starts right here and goes like that. So here's 1. If you revolve it around the x-axis, going all the way out to infinity, you have Gabriel's horn. So the question is, what is the volume of, or inside, however you want to think about it, Gabriel's horn? Okay, all that stuff going all the way out. And secondly, what is the surface area of Gabriel's horn? Okay, I'm not going to give you the answer because I use this for a lot of my students and I don't want to give them an answer, okay? And I guess I don't want to give you either. Anyone who's watching this, you can get it easily enough online, more than likely. But I will give you a couple hints. First of all, remember that to find volume, the easy way here is to use the disk method. Okay, use the disk method, and of course you're going to go all the way out to from 1 to infinity. Okay, and for the and you're gonna I'll tell you. Oh shoot, I'm not going to tell you what happens. Okay, I'm just going to let you find out for yourself. And then the surface area, abbreviated SA. Then remember the formula there. It's something like this, right? It's 2 pi times the value of the function times 2 pi, or you take the value of the function, which is this height right there. If you multiply that by 2 pi, you get the distance around. And then finally, you have to multiply that by this little distance right there. And that little distance right there is that little arc length. And recall that that little arc length is given by that. Okay, let me make sure that I'm still being recorded here. Yep, I am. Okay. So there's the formula for arc length. The distance around times the thickness. Right there, you get that. Now, this also goes from 1 to infinity. Now, here's what you're going to find. This one here, you can evaluate easily enough. You can get an exact answer for it. Right here, you're going to get something which you won't be able to find the antiderivative of. Okay, so that's no good. But what you can do, just through a little reasoning, is you can say this quantity right here, that quantity right there, is always going to be bigger than 1. Agreed? Because you take anything and square it, it's positive, you add it to 1, it's going to be greater than 1. You take the square root of anything bigger than 1, it's going to be bigger than 1. So here's my point. This thing right here, you will find, go ahead and do it. Take this function and do what it says to do. But that's going to be greater than or equal to 1 for all x on this interval. And so, since that's the case, this function is going to be greater than or equal to this function for all x. I keep running out of room here. I need another 6 inches to this board. 1 to infinity. Okay. So that's the case. This is less than that, and this is greater than or equal to that. And then you can again apply something from Calc 1. If you have, and it's just easy enough to realize without going back to any particular theorem, if you have one function which is always greater than or equal to another one on any given interval, then the integral of this function is going to be greater than the integral of that function, right? It's got to be the case. So by looking at this function right here and determining what its integral is, you'll be able to say something about this. I'm not going to tell you anything more except just that hint right there. Okay, so see if you can figure it out. But you're going to get an answer which at first sight doesn't seem to make any sense. But you keep thinking about it, and well, heck, I just don't know where to stop in my talking. Here's what you're going to find. You're going to find that it has finite volume, but it has infinite surface area, okay? And the question is, how can you have an object which has finite volume but infinite surface area? It seems contradictory. And then you think about it, and you think, no, there's no reason that should be. It might be contrary to intuition or common sense, but there's nothing contradictory about it. So you end up with something which has a finite volume but an infinite surface area. But given that, you have to be able to give an answer to this. What if someone says to you, how is that possible? Because if I were to paint something with an infinite surface area, it would take me an infinite amount of paint to paint it. If I have a nice uniform layer of paint over that whole thing, it's certainly going to take an infinite amount of paint to paint it. And yet it takes an infinite amount of paint to paint the thing, maybe on the inside even, but you can fill the whole thing up with a finite amount of paint. They say, how can you have something with an infinite surface area and finite volume, given that then it would be the case you could fill it up with a finite amount of paint, but it would take an infinite amount of paint to paint it. And you have to be able to come up with an answer to that question, okay? So all sorts of interesting things here going on. As soon as you get to infinity, things start really becoming intriguing, and that's why I like this whole topic. Okay, so this is the end of integration, and now we're going to use these ideas to jump off into sequences and series in the next and last main topic of Calc 2 coming up.